Alright, what I'm going to do is go over these 6 questions for the prac that we set up the other week. Just for your information, this is the 4th time I've done it. I have been experiencing severe technical difficulties, so bear with me. Alright, we'll break the video up into 2 parts, questions 1 to 3 here, and then the second part 4 to 6. So, question 1, demonstrate the rule of reflection practically. Alright, demonstrate reflection, we're going to need a beam of light and we're going to need a mirror. And we can set it up at any angle, doesn't matter what angle. It's the relationship that's important. Angle of the incident ray is coming in like this, we mark it, and the point where it hits the mirror is here, and our reflected ray is here. Remove those, connect the dots. Incident ray. Reflected ray. There's something to measure it off, which would be a normal. And so we match up the interface of the two, or of the mirror, the surface of the mirror. Right. 0 degrees is our normal. Now, incident angle of incidence is 10, 15, 16, let's call that 17 degrees, and hopefully we know we should find that this should be the same, and that's close enough to 17 degrees. So our angle of incidence equals angle of reflection. Cool. 1 down. Number 2, demonstrate the phenomenon of refraction. Explain what causes light to bend using terms like speed and optical density. Okay, first part here, let's demonstrate it. Second part is asking you for a worded answer. Refraction. Alright, chunk of perspex, light ray. So all we need to do is just set up a ray of light hitting the perspex at an angle. Just wondering if that's going to make it easier for you to see, but we'll stick with this. So first thing we need to do is let's mark out our block of perspex. Our incident ray is coming in and hitting the perspex here. Now the ray that comes out the other side is here. Comes out there, travels along there. Now the ray that connects them has to be running from here to here. So we can draw that in when we remove the block, which we can do now. Incident ray. This is the ray that's coming out the other side. And the refracted ray is this one. So, perspex, air, and air on the other side here. So what we're really just concentrating on is this part of it here. Now, to show that it bends, we're going to need something to measure it off, and that something's going to have to be a normal. So 0 degrees, we mark that. And there, I should have done both sides. Normal set up. Whichever way we can draw either side of the protractor. Oops. Okay, and that's the angle of refraction, that's the angle of incidence. And we know, because our light's going from a less dense medium to a more dense medium, this angle will be greater than this angle. And if it's not, we've done something very, very strange. Alright, so this angle here is 25, 26, 27 and a half. Let's round that up to 28. with this sort of equipment, there's no point agonising over half degrees. Measure that up. Here we've got from 180 to 170, that's 10 degrees. We'll call that 19 degrees. So 28, 19, that's less than that, which is good because we know it should be. What's the question asking us again? Demonstrate the phenomenon of refraction. We've done that. Explain what causes light to bend using terms like speed and optical density. Alright, well the light bends when it travels through mediums of different densities. So here it's travelling from a less dense medium to a more dense medium. So the speed of light slows down as it goes into the more dense medium and causes the light to bend towards the normal. You can also say the opposite, which is this here, going from a more dense medium to a less dense medium. The speed of light increases and so the light bends away from the normal. Number 3, calculate the absolute refractive index of your sample of perspex. Okay, so we're going to need to use Snell's law here. And Snell's law says that the sine of the angle of incidence divided by the sine of the angle of refraction is equal to the speed of light in the first medium divided by the speed of light in the second medium, velocity 1, velocity 2. It's also equal to the absolute refractive index of the second medium divided by the absolute refractive index of the first medium. Alright, we're not worried about velocity, so we're going to go with this. Now we know this, angle of incidence, angle of refraction, and we know this. In air, we can assume this to be 1. The absolute refractive index is 1. In perspex, the absolute refractive index, well, we don't know. So that's what we're going to work out. So sine of the angle of incidence, sine 28, divided by sine of the angle of refraction, sine 19, is equal to n2 divided by 1. Okay. Anything divided by 1 is, well, the original number. If that's 1,000, divided by 1 is 1,000. If it's 1.2, divided by 1 is 1.2. So we can actually just scrap that, and we can say sine 28. 28 sine is 0.47. 19 sine is 0.33 equals n2. So we're almost there. 0.47 divided by 0.33 equals the absolute refractive index of our bit of perspex, 1.42. Okay, that's questions 1 to 3. I will be back in a sec with questions 4, 5 and